Now we will take a look at one of the most important applications of acetals or ketals. They can be used as protecting groups for aldehydes, ketones, or alcohols. So let me first use an example to illustrate this. Say we want to carry out the reaction to convert 5-hexane 2-on to 5-heptane 2-on. Now, if you look at this conversion, basically we have added one methyl group to the terminal triple bond, right? So from chapter 7, the chapter on alkynes, we've learned this reaction. It's the alkylation reaction to prepare alkynes. And the strategy we use is to first convert the terminal alkyne to its anion. The hydrogen attached to the triple bond is acidic, so we can remove it to give the anion. Then we react the anion with an alkyl halide. So in an SN2 reaction, we use the acetylide anion to replace the halogen on the alkyl halide. So the alkyl group will be attached to the triple bond. Okay, that's our strategy, right? Put the alkyl group on the triple bond. But for this particular molecule, there will be a problem using this reaction, the alkylation reaction. Why? There is another functional group in the molecule, the carbonyl, the ketone carbonyl. Will the ketone carbonyl survive if we have a carbon nucleophile present? The answer is no. We've learned nucleophilic addition of carbon nucleophile, acetylide, to the carbonyl carbon, right? So these two functional groups will react with each other, which means if you want to deproton on the triple bond, then you will get a whole bunch of mixture because the two groups will react. And you won't have any carbanion left to react with the alkyl halide. So if you want this reaction to take place, we need to find a way to cover the carbonyl group. And we can use acetals or ketals. Okay? So our strategy here is first convert the ketone carbonyl to the acetal or the ketal here. We use 1,2-ethanediol. So we make a cyclic ketal. PTSOH here on the arrow is an organic acid. It's called para-toluene sulfonic acid. It's an organic acid used a lot to provide the acidic environment. Okay, so this is our first step. Then we don't have the carbonyl anymore. Now we can carry out the deprotonation reaction on the triple bond and then the SN2 reaction to alkylate on the triple bond. After the reaction is done, because the acetals and ketals can be hydrolyzed, So we subject the molecule to acidic condition. Then the ketone, carbonyl, is obtained, is recovered. All right. So we have 4 steps in this series of the reactions. The first step is the protection. We add acetal to protect the carbonyl. Step 2 and 3 are the desired reaction, the reaction we want to carry out initially. And the last step is called deprotection. Okay, so this whole process gives you an idea why we want to use a protecting group, right? So we want to convert one reactive functional group into another that does not interfere with the desired reaction. And the new blocking group is called a protecting group. So acetal, or the ketal here, is our protecting group. Then we carry out the desired reaction. Lastly, we need to remove the protecting group. There are some requirements for the protecting groups. The protecting groups need to be introduced and removed readily. We don't need them in our final product. They need to be removed. So if you put on a protecting group that cannot be removed, it's not going to work. And the protecting groups have to be inert to the reaction condition. For example, our acetal or the ketal, they can be hydrolyzed under acidic condition, but they are very stable in basic condition. In our desired reaction, we use sodium amide to deprotonate on the triple bond. That's under basic condition. So our protecting groups will not be affected. All right? So let me give you one more examples here. So this is the reaction we want to do. If you compare the starting material and the product, you see that starting material has 6 carbons. The product has 8 carbons. So we have added 2 more carbons. We need to make a new carbon-carbon bond. And this carbon-carbon bond is made right next to an OH group, right? So we are making a carbon-carbon bond and an alcohol at the same time. Our starting material is an alkyl halide. So that reminds me of the Grignard reaction. Grignard makes alcohols from alkyl halides, right? So if we break the bond indicated here, on one side we need the alkyl halide, which is exactly the alkyl halide we have as a starting material. On the other half, we have the OH containing part. And remember, you want to convert that to a carbonyl, right? So the strategy here, we can convert the alkyl halide to the Grignard reagent. Then react the Grignard reagent with the 2 carbon aldehydes. Then we should be able to get our final product. The thinking is correct here, right? But there is a problem. What's the problem? Take a look at other functional groups present in the molecule. We have 2 OH groups. will Grignard survive with acidic protons? No. Right? We've learned before that Grignard reagents are strongly basic. So any acidic proton can react with Grignard. It's a carbanion. It can take the acidic proton to make the alkane. So with the two alcohol molecule present, we are not able to make the Grignard reagent to react with the aldehyde. Before we do the Grignard reaction, we will need to protect the two OH groups. To protect vicinal diols like this, we can use acetals or ketals. So now we need a ketone to react with these two OH groups, right? So the strategy we will use is to react with acetone. Two OH groups react with the same acetone carbonyl. Then we will form a cyclic ketal in this case. This cyclic ketal protects the two OH groups. Then we can convert the halide to Grignard reagent. React the Grignard reagent with the aldehydes to make our new carbon-carbon bond. Then after the reaction, we can hydrolyze the acetal or ketal back to two OH groups. So we have added a protection group and we have to deprotect it. Okay, that's the overall reaction to convert our study material to the desired product.